Hey, good to see everyone again. We're starting a new unit today, and it's a unit that focuses on modern atomic theory, the idea that all matter is made up of tiny particles that cannot be broken down into anything simpler. That modern atomic theory, though, is modern. It's only been around for a couple of hundred years. And for the vast majority of human history, people didn't really think of matter as being made up of very, very small particles that we call atoms. There's one real exception to that. A few hundred years before our current era, there in ancient Greece were a couple of philosophers, one of which you've certainly heard of, Aristotle, and the other who you may not have heard of, Democritus, who had an argument about the nature of matter. And they had very different opinions about what composed matter. Aristotle was of the opinion that matter was continuous, and Democritus was of the opinion that matter was finite. Here's one thing that both had going against them. Neither one were scientists. They weren't performing experiments. Their arguments were based in logic, but they had no evidence for their arguments. And so the argument really came down to who did you want to believe, or who made the best argument moving forward. Let's talk about the idea of matter being continuous, which is what Aristotle proposed. I think the best way you could think of it is, let's say you had a piece of paper, and I'll just sketch that out. And that piece of paper was just like a regular notebook paper. And you decided to take that piece of paper and to cut it in half and discard half of it. So let's say you cut it in half, and what you're left with is half of what you originally started with. And so now you have half a piece of paper. Well, Aristotle argued that you could continue to do this same process over and over again continuously and continue to cut the piece of paper in half, and what would remain is half of what you began with. Aristotle saw no end to this process, that you could continually cut the piece of paper in half and have half remaining. And there would eventually you would be dealing with very small pieces of paper, but theoretically there should be no end to that process. Always half would remain. That's what he meant by the idea of matter being continuous. There was no smallest piece of matter. On the other hand, Democritus proposed that eventually, if you were doing this same thought experiment, and you kept continually cutting the piece of paper in half, discarding one half and keeping the other, that eventually you would get down to the smallest piece of paper possible. And that smallest piece of paper possible, which couldn't be broken down any further, was what he called atomos, obviously where our word atom is derived from. It's just this idea that matter is finite, and eventually you will get down to the smallest pieces that can't be broken down any further. Now, that said, as I said in the beginning, there was no evidence to support either one of these ideas. And it turns out that for, popular opinion's sake, Aristotle won the argument. And so for a couple of thousand years, the idea of matter being continuous really prevailed, and there was no talk really of atoms. That began to change, in the 1800s, and eventually culminated in our modern atomic theory that was first proposed by John Dalton. But for a couple of thousand years, we didn't have that idea. Didn't mean that we didn't know a lot about the matter that surrounded us here on Earth. So for the longest time, elements have been known. You could even say long before the Greeks, thousands of years before the Greeks, people would have known about some of the elements, things like copper, things like lead, gold, silver, on and on. Most of them happen to be metals. Most of them happen to be things that you could dig out of the ground and not have to break down in any way. And so you had about, I'd say, around 20 elements or so that have been known since antiquity for a very, very long time. But it really wasn't until maybe the mid 1600s and early 1700s that the total number of elements that were known began to expand. Today, we know of 118 elements. And so, how did we get from 20 elements from antiquity up to 118 today? Well, that was a process, and it took a very, very long time. One of the things that I think really led to kind of this revolution in the understanding of the chemical elements was just kind of the organizational skills of scientists, especially around the 1700s and 1800s. I think it was in the mid 1700s that a scientist named Lavoisier first kind of put together a list of the elements that were known at the time. Something like 33 elements were known at the time of Lavoisier. And about 100 years later, really what started to come together is what we think of as a periodic table happened in the late 1800s by a Russian scientist named Dmitry Mendeleev. He's often referred to as the father of the periodic table. And no, he wasn't the first one to put a periodic table or list together, but he's the first one to do it in a way that kind of coincides with what our modern periodic table looks like. So he organized his chart in a couple of ways. He organized it first by what we would call relative mass. And relative mass is essentially kind of how the weight of each element compared to the weights of the other elements that were known at the time. The second thing that he did, which was pretty innovative, was he stacked elements on top of one another if they had very similar chemical and physical properties. And so if I look over here in this, this first column right here, I've got lithium and sodium and potassium. These are all elements that were known to be very similar to one another. They reacted in similar ways. They had similar properties as well. And so he's got these two organizational methods, and he did something further that I think really kind of explains why element discovery really happened to a large degree in this time period. He started to leave gaps in his periodic table. So we've got a couple of examples right here and right here, modern day gallium and modern day germanium. They were unknown at the time of Dmitry Mendeleev, but he recognized that with the elements that he did know, nothing really fit into the columns with boron and aluminum or with carbon and silicon. So he proposed the idea that he leave a gap, essentially, and that these elements should exist, and based on the properties of the elements in the column that these elements should be in, he was able to make some predictions about what those elements would look like. So he predicted things like the relative mass of the element, the density of the element, what its melting point should look like, that kind of thing. Different physical properties that one could then go out and look for. And that's what I think is really the power of his periodic table, that it allowed scientists to know what to look for, and therefore led to the discovery of a number of elements. So when gallium, for instance, was actually observed for the first time, its relative mass was very close to the prediction of Mendeleev. The density was exactly the same. It has such a low melting point that it melts in your hand. Okay, so he's giving scientists a list of things to look for, and they go out and they find those things. Speaking of a list, that list would contain things that we're very familiar with at this point. You're talking about looking for physical properties, especially intensive physical properties, properties that don't change depending on how much of the substance you have, and then chemical properties as well. So he's predicting and specifying a number of chemical properties and uh, intensive physical properties that one could go look out for. And eventually we work our way up to 118 elements. Now, the truth is that today, the number of elements that we have is 118. And the last one that was discovered was in 2009. It's number 117. It isn't even labeled on this version of the periodic table that I have right here. It's the element tennessine, which was kind of discovered or really manufactured or synthesized by scientists in both Tennessee and Russia, amongst other places. So our modern periodic table, there's no reason to think that it's done or it's complete. It's an ever evolving diagram and tool that we use that we can really consider to be kind of a living document of sorts, in that it is ever expanding. Okay, we're going to come back and talk about today's periodic table and ways that we differentiate elements within that periodic table, but we'll save that for our next video. See you then.